So at first, we will start with some basic explanation of what a motor unit or pulse train is and how do we assess its accuracy. So when we calculate or when we estimate a motor unit filter and we apply it to the EMG signal, we get a motor unit pulse train, which is depicted here. So we can see that pulse train consists of pulses that are part of motor unit's firings, and usually noise is present, which is depicted here.
Please use the laser so that also people online see what you are porting.
Our laser is
like this one.
Okay, thank you. Usually noise is also present in the pulse train, and that noise can be either physiological, so like in this example here, where it's caused by the crosstalk from other motor units, or in some other cases, it can be instrumental, or it can be caused by poor skin to electrode contact. When we are expecting the pulse train, we usually look for the consistency of the heights of motor unit pulses. If there is no consistency, either we have something very strange going on, or it can be further explained by expecting the experimental protocol or more or have a deeper knowledge of what is going on with the motor unit and why it's behaving that way. So Aleš already mentioned today the pulse to noise ratio, which is calculated using this equation here. And we can see that pulse to noise ratio is taking into account the segmented motor unit pulses, their energy, and it compares it to the energy of noise. So pulse to noise ratio, as already mentioned by Aleš, is positively correlated with sensitivity and precision and negatively correlated with the false alarm rate. So it gives us a pretty good, it's a pretty good matrix of how accurately a motor unit was identified. But can we really trust it? I mean, it's a good metric, but it can be deceiving, like in this example over here. We decided that this motor unit was identified with high accuracy. It was not. But even though we can see that motor unit was not identified with high accuracy, pulse to noise ratio will be very high because those pulses that are over here are very high in amplitude and their energy will be still much greater than the energy of noise here. I have prepared some examples on the simulated signals later in the hands-on training, so you will actually be able to see those examples in real motor units. Besides pulse train, the automatic part of the decomposition also produces firings, which are yielded by the automatic segmentation method. So with firing, we denote a pulse train as being a true pulse from a motor unit. So with firings, we actually make a division between motor unit pulses and noise. So that's why this is important. But always keep in mind that the composition algorithm, so the automatic part of the decomposition, does not know anything about the recording, about the subjects, about our protocol, what's the tension of our studies, and so on. And that's why we always need to manually inspect all the motor units and edit them. When we correct all the firings, so when we optimize the firing pattern, we have this firing pattern as is depicted here. And regarding the firing pattern, we usually look at the inter-discharge interval and at the instantaneous discharge rate. So we are able to explain the motor unit behavior more accurately. We usually also inspect the force signal along with the pulse train and the firing rate, because there is some expected changes during the when we are slowly increasing or decreasing force, and we also expect the more consistency during the hold of the force phase. Here is also one very important thing, and this is the first firing, because based on the first firing, we are able to identify the motor unit recruitment threshold. Motor unit recruitment threshold is a value of force that is needed for a motor unit to recruit, so to activate, in other words. Based on that, about that first firing, I can tell you something that I think is pretty interesting. We are doing a research on manually editing the decomposition results and how it differs when we accumulate different operators with different level of experience and also different type of signals. And the only scenario where there was a significant difference between different level of expertise of human operators was when we were looking for the accuracy of identified first firing. We were also researching the rate of agreement, normalized rhythmic square disagreement, the editing time, number of used actions, and so on. And the level of expertise was never a significant factor, except when we inspected the first firing. So finding the true first firing is a challenge, and it can be difficult, and you need to have a lot of knowledge and a lot of experience. We can see different behavior of a motor unit crosstalk in these two examples. So in the first example here, we can see that crosstalk is pretty constant, and here it's increasing. We know that when we are increasing the force, so when we are increasing the contraction level, also the crosstalk will be increased. So if we would now depict force signal here, it would look like that. So in the first signal, we have a constant excitation, and in the other example, we have increasing excitation. As already mentioned before, some changes in motor unit pulse train height are expected, especially during fatigue and dynamic contractions. In the first example, we have fatigue contraction, and we can see that the motor unit pulse train had pretty much the same amplitude till the 8th second, and after that, it slowly decreased. That's because motor unit got a bit tired, and when motor unit is becoming more and more fatigued, it also changes its move-up shapes. And as Aleš already mentioned, motor unit filter is based on a move-up shape. So when I say move-up, I mean motor unit action potential. Okay, so don't get confused. And the bigger the mismatch between motor unit filter and the motor unit action potential, the smaller the pulse train. So we can see that motor unit filter was probably accumulated from a move-up shape that was present more at the beginning, so at the first half of the signal, and then when move-up shape was changing more and more and more, there was a bigger mismatch between filter and move-up shape, so the pulse train was a bit smaller in height. In dynamic contraction, same thing happens, but not because of fatigue, but because muscle is shortening. So shortening also influences the move-up shape. And here we can see that move-up shape was changing almost uniformly through the whole signal. In isometric contractions, also some smaller changes in amplitude of pulse train are expected, especially during the phase when we are slowly increasing or decreasing the contraction level. So here we can see an example of a trapezoidal experimental protocol. And here we can see the ramp up phase, hold phase, and ramp down phase. And the same for the muscle gastrocnemius medialis. Gastrocnemius medialis is a pinnated muscle, while vastus lateralis is a fusiform muscle. And fusiform muscles demonstrate bigger change in amplitude during increasing contraction. Sometimes a crosstalk can be so high that it masks the true firings of a motor unit. And that's when we are starting to lose motor unit. We can try to resolve it, and I will show you that later in hands-on training, but what we do in this scenario, we add firings above certain thresholds, so we usually just denote the higher pulses. We delete firings that are lower in amplitude, and then we recalculate and reapply a motor unit filter, which results in new version of a pulse trend. And we can repeat those steps over and over, but only 3 things can happen in this case. Usually, one of those 3 things. Either it will get us nowhere, so we will still have a mess. Either we'll identify a motor unit that was already identified before, so we will just have a duplicated motor unit, which will later be deleted anyway. Or the most dangerous situation there is, we will synthetically create a motor unit that never existed, the subject. So that's why you should never edit one motor unit too much. For you who, Aleš, was your mentor when you were learning how to edit the motor, how to edit the results of the decomposition, I guess you are all familiar with the phrase, just be brutal. Even though we have some experimental protocols and we were able to identify a small amount of motor units, we still need to be brutal and delete motor units that are identified with poor accuracy. And you should always consider 5 different things when you are considering motor units for deletion. So at first, you need to look at the pulse to noise ratio. And if it's low, then you should consider this motor unit to delete. If you have a lot of different heights of amplitude in the pulse frame, this is also an indication that motor unit was poorly identified. You should always inspect the motor unit action potential shapes. And MOAB shapes are also very important if we have a power line noise. Because if we don't remove it before the decomposition, I don't know if you remember from the summer school in Maribor, but if you don't remove the power line noise from the signal and you have it and you decompose it along with real EMG data, power line noise will show as another motor unit, which can be very easily identified by just looking at the MOAB shapes. We also need to look at the instantaneous discharge rate panel. We need to have a clear firing pattern during ramp up, hold, ramp down phases. And we should also look at the number of firings that motor unit has. So here we have an example of motor unit that should be deleted. So we can see that MOAB shapes are pretty strange. Pulse to noise ratio is 27.5 decibels, which is higher than 24, but still not very high pulse to noise ratio. Instantaneous discharge rate doesn't have a pattern at all. Firings are just splattered and everywhere. And pulse train is also very strange. We have a lot of different heights. So we have a lot of irregularities. So this motor unit was very poorly identified and should be deleted so it won't mess with our analysis after. Aleš already presented the segment D today, but we will now pay more attention to each of those 5 steps. segment D, or all those 5 steps in segment D, are at our university done manually using the DEMUSE tool, and more specifically, the CKC inspector in the DEMUSE tool, which is a separate window. During today's hands-on training, I will actually show you the DEMUSE tool itself and the CKC inspector, and we will together edit some of the signals. So in the CKC inspector, we have 3 different panels. We see motor unit action potentials. We can see the instantaneous discharge rate along with recorded force signal in this example. And we can also see the pulse train depicted here with blue line and firings with red dots. The easiest way to start, and so the simplest case, is when you're having duplicated firings. So here we have outliers, which can be either identified in the middle panel by those firings who are much faster than their neighboring firings, or you can identify them in the lower panel where those very little spikes have firings. We resolve the outliers by removing them, and it will result in that kind of motor unit. The second situation that will occur during editing are missing firings, and we resolve them by adding them. We can spot the missing firings by looking at the middle panel, where we can see firings being very slower than the rest of them, or you can see here some pulses without firings. But when we are adding the missing firings, we need to be careful, because even though crosstalk usually results in very small pulses, that is not always the case. We know that when we are increasing the contraction level, we are also increasing the crosstalk. And because of that, bigger number of motor units are active. And it could randomly happen for 2 motor units to get synchronized in one moment of time. And this will result in a very big pulse. So even though a pulse is big, it doesn't mean that it actually belongs to a motor unit that we are inspecting at the moment. It can still be caused by crosstalk. So we need to be careful. And when we are considering whether a pulse is actually belonging to a certain motor unit, like in this example here, we can do a very simple test. We can at first look at the pulse, and then we press the reinforce button. Reinforce button estimates and reapply motor unit filter to the EMG signal, so it recalculates the pulse train. So we will get a newer version of pulse train. So that is reinforce. And we then inspect the amplitude of the pulse train. And then we add the firing that we are inspecting, and we hit the reinforce button again. And if that pulse increased in amplitude, so the amplitude is pretty much consistent with the rest of the pulse train, then we are safe to say that this pulse probably belongs to that current motor unit. That procedure, that test, is also used in the semi-automatic method that I will show you later on. Well, the iterative spike-based motor unit optimization is what I already said. It's just we hit a reinforce button, so motor unit filter is re-estimated and reapplied to AMG, and we, as a result, get a new version of pulse train. As Aleš already explained, when 2 or more motor units are very similar in move shapes, the automatic part of the composition sees them as being the part of the same motor unit, and we get a merged motor unit. So in this example, we can see one motor unit with pretty high spikes and another motor unit here. And we can resolve those merged motor units by subtracting them. And in this case, we would get motor unit 1 and motor unit 2. what is happening here? This is a rather very special case. Now that I will explain this, keep in mind that we still have isometric contractions, because this exact situation we will see today 3 times. First time is now in isometric contractions. The second time it will be during the hands-on training in fatigue signals, and third time in dynamic signals. And there are 3 completely different behaviors of motor unit, even though in the sequencing inspector it looks exactly the same. So we have an isometric contraction. So what is happening here with the motor unit? Motor unit de-recruited and re-recruited again. So beginners usually make a mistake by adding those firings here in between. But motor unit was actually not active for this short time period. So adding those firings in the middle would be wrong. Because we will work with simulated data today, we also know the ground truth of firings. And this will come in very handy when we will inspect the accuracy of our manual editing. So here we have a ground truth, and here we have edited pulse frame that we edited. And we can see that those firings that are the same in both cases are here acknowledged as being true positive firings. Here we have a false positive firing because it shouldn't be denoted, as we can see it here in the ground truth. And here we have a false negative firing because it should be denoted, but it's actually not. So this is the semi-automatic method to access the accuracy of firings being denoted as good, bad, or neutral. So here, that method uses the same approach as I showed before. So you select some of the firing as witnesses, and then you look at the testing firing or its amplitude. And then you recalculate and reapply the motor unit filter, and you observe the amplitude. And after that, you add or you denote the testing firing as being true firing. And you again recalculate and reapply the motor unit filter. And if that tested pulse increased significantly, that pulse is denoted as good. If it decreased significantly, it's denoted as bad. Otherwise, it's just neutral. So in this example, I'll show you again.
If the witnesses reacted.
Yes, if the witnesses, yes.
You observe the witnesses, not the tested parts.
No.
Okay?
Yeah, thank you.
Yeah.
Thank you. So here we can see the result of this method, and we can see that results are pretty good, even though they're not perfect. Here we can see one firing, which was denoted as bad, even though it should be good. And we can see that crosstalk was identified correctly. And here at the beginning, as it is a challenge for human operators to find the true first firing, it's also a challenge for algorithms to identify it. We can see that those firings here are denoted as neutral. Here we can see another example of motor unit of the results of that method, and another where we can see that the recruitment and re-recruitment situation was denoted correctly by this method, because those firings in the middle are not accumulated. So we've talked about how we optimize one motor unit filter and how to deal with one motor unit at the same time, one motor unit filter, one pulse train, and so on. But what about if we would like to concatenate 2 or more signals? So if we would like to see the same motor unit in different contraction levels? Or what about if we would like to track the same motor unit before and after an intervention? So the idea here is to estimate a motor unit filter in one signal and to apply it on another signal. So here we have an example where we estimated motor unit filter at 40% contraction, and we apply it to the 70% contraction. And the number of successfully tracked motor units was 17. So, and if you look at the pulse train and at the motor unit firing rate, you can see that there is a lot of differences. But even though we were able to successfully track 17 motor units. Here, I would like you to keep in mind that tracking is just tracking. You are not able to find any new motor units when you reapply motor unit filter. You're just able to find a pulse train from the same motor unit that was already identified in previous case. Here we have an example where we estimated and applied motor unit filter on different contraction. So we can see that tracking of motor units was the most successful when we were estimating and applying it on the same contraction level. And the biggest the difference between the contraction level where we estimated the motor unit and where we apply it, the smaller the number of successfully tracked motor units. And I would like you to look at the first line here. And if we look at it in this direction, what we did here is we estimated the motor unit filter at 10% contraction, and then we apply it to all highest contraction level. And we can see that number of successfully tracked motor units was decreasing. We were losing motor units. And why that happened? Well, as we said before, when we are increasing the contraction level, also the crosstalk will be increased. And that's why tracking of motor units from lower to bigger contraction level can be a big challenge, because crosstalk is also increasing and identification of motor unit is becoming much harder. Now, if we look at the last line here, where we look at it in this direction, we estimated a motor unit filter at 70% contraction level, and we apply it to lower contraction level. And we were losing motor units again. Quite frustrating. And this happened because of the Hahnemann's principle. We know that the recruitment order of motor units is, at first they will recruit the smallest motor units and then the bigger ones, and last the biggest. So what happened here is that we identified only high threshold motor units that were actually not active in the lower contraction levels. And that's why here in the last line, we were losing contractions. But the FDI muscle has least difficulties with those two principles. It's the best muscle to track among three that I will show you. So the next muscle is tibialis anterior. And we can see that the crosstalk and the Hahnemann principle took bigger toll here. And last, the biceps brachii muscle was even more difficult to track. So, to sum up a little bit and maybe to prepare you for the hands-on training, everything that you just saw is able to do with the DEMUSE tool. And you will get to know it today along with the CTC inspector and with the application with which you can inspect the accuracy of your own editing.